Thank you for having me. So I have no disclosures. For background, operating on patients with infiltrative brain tumors in the dominant hemisphere sometimes induces permanent impairments in language function. There's a large body of research showing that this significantly decreases both quality of life and survival. The neuroanatomical origins of these deficits remain unclear. Even in healthy individuals, the neuroanatomy of language processing is not well understood. This problem is significantly exacerbated in glioma patients who demonstrate significant inter-individual variability in functional anatomy. Surgeons use direct stimulation intraoperatively on awake patients to map language function. This is the gold standard right now for making surgical decisions. They correlate real-time task performance with inhibitory stimulation to identify cortical and subcortical sites necessary for language. However, it's an imperfect technique. Its invasive nature precludes its use for patient selection and surgical planning. Temporal constraints prohibit comprehensive mapping, and comorbidities exclude many patients. Patients are continuing to sustain deficits. Transcranial magnetic stimulation is a non-invasive method for mapping cortical language function. It works very similarly to intraoperative mapping, but can apply stimulation through the skull in an outpatient setting. It's a new technique, though, and unproven with regards to language. Multiple previous studies have shown that many TMS language positive sites are false positives, and this is in comparison with direct stimulation intraoperatively. So here we aim to develop an approach for non-invasively localizing essential language function to predict and avoid aphasic deficits using TMS language mappings and routinely available preoperative imaging. And by essential, we mean regions that will lead to permanent impairment if resected. So the study included 79 consecutive glioma patients undergoing surgery in the dominant hemisphere. This is the same cohort of patients selected for standard of care language mapping at our institution. Patients underwent TMS mapping and TMS-based fiber tracking and formal language evaluations preoperatively and in 1 to 3 months postoperatively. So this diagram right here shows the workflow for a patient with a tumor in the inferior frontal lobe. So you can see the row A has a tumor. Row B shows the grid that's placed over the tumor. A 1 centimeter grid of stimulation targets is applied around the tumor, and each point is stimulated to identify the language positive sites on the grid. And these positive points are then used as the cortical seed for fiber tracking, which you can see in row D here. An FA threshold, fractional anisotropic threshold for fiber tracking was standardized to the individual anisotropic profile of each patient. For each patient, the threshold was incrementally increased by 0.01 until no more fibers were generated. This was defined as 100%. This number was defined as 100% for that patient, and mapping was done at 25%, 50%, and 75% to identify the optimal percentage across the whole cohort. The resection of TMS points and fiber tracks were correlated with long-term aphasic deficits. So our initial analyses showed the functionality of TMS points depended on their subcortical connectivity profile. The plots on the top right show how the subcortical connectivity profile of TMS points affects their predictive value for deficits if resected. And this plot here refers back to the percentage approach that I mentioned in the last slide. So you can see right here, TMS points alone are not significantly predictive, but then TMS points with connecting tracks identified at certain FA threshold percentages get more and more predictive, with 75% being the most predictive. Stratification of TMS points by subcortical connectivity profile defined a canonical cortical distribution of language sites. The bottom right figure shows that TMS points distribute homogenously throughout the left hemisphere. So in the top left of the bottom right shows this homogeneous distribution of TMS points, while TMS points with strong subcortical connectivity on the top right shows a much more localized perisylvian distribution consistent with canonical cortical language networks. You can see there are hotspots for the TMS points with strong subcortical connecting tracks. Hotspots emerged in the inferior frontal lobe, the ventral precentral gyrus, and the posterior superior temporal gyrus. And this recreates a distribution that was derived from the largest study of invasive cortical mapping to date. So we then show that the tracks localized by TMS language sites recapitulate normative patterns of subcortical connectivity at a group level. The left figures show that the probabilistic distribution of TMS tracks in MNI space show hotspots within the volume of normative tracks canonically associated with language derived from the Human Connectome Project. The arcuate fasciculus, the IFOF, the ILF, the SLF, the uncinate fasciculus, and the frontal ascending tract. The top right figure shows that the highest voxel intensities of both the probabilistic TMS tracks and population average normative tracks localized at the same posterior temporoparietal segment of the arcuate fasciculus. The bottom right figure shows that the SLF portion of the probabilistic TMS tracks show the same pattern as the population averaged SLF volume from the Human Connectome Project. Much lower voxel intensities anterior to the precentral gyrus, demonstrating significant inter-individual variability in this region. So this fiber tracking approach was based on individual cortical function, is completely data-driven, which is significant because current fiber tracking approaches used for tumor surgery are extremely subjective and need to be done by an expert, which limits both reproducibility and accessibility. So the resection of TMS tracks predicted aphasic deficits independently of cortical damage, defined by the most predictive connectivity subgroup of TMS points. The top right figure shows that adding subcortical data to the cortical predictive model decreases odds ratio from 9 to less than 1, while adding cortical data to the subcortical model did not significantly alter its predictive value. The bottom right figure shows a confusion matrix depicting the predictive value of resecting TMS tracks. The negative predictive value was 98%, but the positive predictive value was 50%. And this indicated to us that the resection of TMS tracks needs further classification for optimal predictions. So we then segmented the resected portion of TMS tracks in each patient, classified them according to functional outcome, and normalized them to MNI space. So true positives were defined as tract resection plus corresponding deficit. False positives were defined as tract resection plus no deficit. True positive tract cavity segmentations co-localize with normative white matter tracts derived from the Human Connectome Project, in contrast to false positive tract cavity segmentations. The middle right figure shows significant differences in measures of spatial association with normative tracts between true positive tract cavity segmentations and false positive segmentations. The figure below that shows how each normative tract contributes to classifying true positives versus false positive tract cavity segmentations. The very bottom right figure shows a grid search to derive optimal cutoffs from measures of spatial association between TMS tracts and normative tracts to further classify TMS tract resections and improve overall outcome predictions. We then warped these normative tract volumes from the Human Connectome Project to patient space for the whole cohort to further classify individual resections of TMS tracts and increase the positive predictive value of the model. In this final model, patients who did not have TMS tracts resected were automatically classified as safe outcomes, while normative tracts were used to determine which TMS tract resections would lead to aphasic deficits. This led to an accuracy of 94%. The top right plot shows the increasing predictive value for each iteration of the predictive model in terms of odds ratios. TMS points first, then TMS points stratified by subcortical connectivity, TMS tracts, and finally TMS tracts combined with normative tracts warped to patient space. The final model had an odds ratio of 134 for a positive prediction. We then applied this approach prospectively to a glioma patient undergoing surgery in the dominant hemisphere. The patient first received TMS mapping. Data-driven fiber tracking was done based on this patient's TMS mapping. The normative volume of language-associated tracts were warped to patient space and overlaid with individualized TMS tracts. Regions of co-localization between normative and individualized tracts were segmented to produce a spatial prediction for essential language function consistent with the pathway of the middle longitudinal fasciculus. Intraoperative direct subcortical stimulation was performed correlated with real-time task performance. You can see here in the flow chart that the first 6 focal sites of stimulation were negative, meaning that they produced no errors in task performance. These negative points were all more than 5 millimeters away from the preoperative reconstruction. Seventh side of stimulation produced reproducible semantic errors localizing the region of co-localization between TMS and normative tracks at a distance of 0 millimeters. The resection was stopped here, preserving the region of co-localization accurately corresponding with preserved postoperative language function. And so in conclusion, long-term surgical deficits in language processing result from subcortical damage to subregions within the normative volume of association white matter tracts. TMS language mapping, diffusion-weighted imaging, and normative data localizes essential language function and predicts the functional impact of tumor surgery with an accuracy of 94%. And so I don't have a slide for it, but for acknowledgements, the TMS team, MD Anderson, Dr. Prabhu, and Dr. Prinsloo couldn't have done this without them. So very thankful. And any questions?
All right, thanks a lot, Matthew. There don't seem to be questions in the app yet, so let me ask one. Can you elaborate again on how TMS mapping was performed exactly? So what is a TMS point, as you call it?
So let's go back to the figure. So for each tumor, there's a grid, a 1 centimeter spaced grid that's overlaid onto the tumor. That's in row B right here. And then this grid comprises, these are the stimulation targets for the stimulation. And so each point on the grid is stimulated in correlation with a language task performance for an object naming paradigm. And so if a patient has a speech arrest or an error at a particular point on the stimulation, then that site is marked as language positive. Does that make more sense? So the idea is that a subset of these points on the grid will be identified as language positive based on the patient's performance when that point was being stimulated with inhibitory stimulation.
Thank you. I just have two related questions. Firstly, is this cohort of patients for people with low-grade gliomas, I presume, or are they mixed grade, some
Mixed.
low-grade?
It's both low-grade and high-grade, yep.
So then that begs the question, if it's low-grade, how much of those stimulation points do you think is maybe related to tumor infiltration and remodeling and plasticity-related mechanisms, which is why you see such a broad range of stimulation points across wide anatomical range?
Yeah, I think that's possible, yeah.
And then secondly, do you then see a difference between the high grade and the low grades?
In terms of TMS point distribution?
Exactly.
That's a good question. We haven't analyzed that. It's a really good question. I think the distribution of TMS points, let's see. So right here, I think the reason that there's really the functionality of the TMS points that led us to believe that a lot of them are false positives, if that's your question. I think that you're right that in especially low-grade glioma patients, that there could theoretically be cortical language sites pretty much across the left hemisphere, which has been demonstrated in multiple previous studies. And so we didn't conclude that those TMS sites were non-functional or false positives because of their abnormal anatomical localization, but more because of previous studies comparing it with direct stimulation, and then also in this study comparing their resection with functional outcomes.
And then just very quickly, how many of these patients do you think if at 6 months they have a language deficit, they will have a permanent?
Yeah. So the formal evaluations were at 1 to 3 months. We didn't have 6-month formal evaluations. I didn't put this in the slide, but in the paper we specified that every patient with a deficit was followed clinically for 6 months. And so there will be subjective comparisons to the previous formal language evaluation. And so from that analysis, every single patient that had deficits at the 1 to 3 month mark persisted through the 6-month mark as well.
Okay, all right, thank you.
Thank you very much.